there's something out there, something massive, something that's been pulling at the edge of our solar system for billions of years, warping the paths of distant objects in ways that shouldn't be possible. And we can't see it, not yet, but the math says it has to be there. The orbits say it has to be there. The survival of certain objects that should have been ejected into deep space millions of years ago says it has to be there. This isn't about speculation anymore. We're past the point of asking whether a ninth planet exists. We're now in the phase of trying to prove what we already know must be true, and that search has entered its most critical stage. The outer reaches of our solar system are behaving as if something approximately 5 times the mass of Earth is exerting a gravitational pull from a distance so vast that sunlight takes nearly a full day to reach it. These aren't subtle effects. The clustering of distant icy objects beyond Neptune exhibits a specific non-random pattern that our current 8-planet model cannot explain. When astronomers calculate the probability of this alignment occurring, by pure chance, the number they arrive at is less than 0.1%. In scientific terms, that's not just unlikely. That's a signature, a fingerprint, the kind of evidence that demands an explanation. And the only explanation that fits the data is the presence of a massive object we haven't detected yet for decades. This evidence has been building quietly in the background of astronomy. It began with small anomalies, objects that were slightly out of place, orbits that didn't quite match predictions. But as our telescopes improved and our surveys expanded, those anomalies stopped looking random. They started forming a pattern, and that pattern pointed toward a single, inescapable conclusion. There's a planet out there that's larger than Earth, sitting in an orbit so elongated and so distant that it takes somewhere between 10,000 and 20,000 years to complete a single trip around the Sun. At its closest approach, it would still be 200 times farther from the Sun than Earth is. At its most distant point, it could be 1,000 astronomical units away, drifting through a region of space so dark and cold that it's functionally invisible to most of our instruments. This is not the first time we've found a planet without seeing it first. In fact, the most dramatic planetary discovery in history happened on a piece of paper before it happened through a telescope. In 1846, a French mathematician named Urbain Le Verrier was studying the orbit of Uranus and noticed something wrong. The planet was accelerating and decelerating in ways that Isaac Newton's laws of motion could not account for. Uranus was being pulled. Something massive was tugging at it from beyond the known edge of the solar system. Le Verrier didn't have a telescope powerful enough to see this invisible force, but he had mathematics. He calculated where the unseen planet should be based purely on the gravitational distortions it was causing. He wrote down a set of coordinates and sent them to astronomers at the Berlin Observatory. They pointed their telescope at that exact location, and within 1 degree of Le Verrier's prediction, they found Neptune. This discovery established a precedent that has guided planetary science ever since. Gravity acts as a tracer for objects we cannot yet see. If something is massive enough, it leaves evidence of its existence in the motion of everything around it. You don't need to observe the object directly. You just need to observe what it's doing to its surroundings. And right now, the outer solar system is showing clear signs of being influenced by something we haven't accounted for. We are, in every meaningful sense, in a second Le Verrier moment. The evidence for Planet 9 is not visual, it's gravitational, and it's becoming harder and harder to ignore. The modern search for this planet began in earnest when astronomers started paying closer attention to a specific category of objects, known as scattered disk objects, or SED. These are icy bodies that orbit far beyond Neptune in a region of space so remote that they barely interact with the known planets. In a stable 8-planet system, the orbits of these objects should be oriented at random angles. Billions of years of chaotic gravitational interactions should have scattered them in every direction, but that's not what we see. Instead, these objects are clustered, their orbits are aligned, they're moving in the same general direction, tilted at similar angles, and their closest approaches to the Sun all point toward the same region of the sky. This is not normal, this is not random, and it demands an explanation. In 2016, 2 astronomers at Caltech, Konstantin Bettigen and Mike Brown, published a paper that changed the conversation. They built a mathematical model of the outer solar system and ran thousands of simulations to see if the clustering could be explained by the gravitational influence of the 8 known planets. It couldn't. No matter how they adjusted the parameters, the 8-planet model failed to reproduce the observed pattern. But when they added a 9th planet to the simulation, everything clicked into place. A world roughly 5 to 10 times the mass of Earth, sitting on a highly elongated orbit, would naturally shepherd these smaller objects into precisely the kind of synchronized paths we're seeing. The math worked, the physics worked, and suddenly, the idea of a 9th planet shifted from fringe speculation to a legitimate hypothesis, backed by peer-reviewed research. This hypothetical planet would not be where most people imagine when they think of the solar system. It wouldn't be sitting neatly between the orbits of the known planets. It would be out in the deep dark, far beyond the Kuiper Belt, in a region where the sun is just another bright star in the sky. Its orbit would be so elongated that it would spend most of its time at extreme distances, only occasionally swinging closer to the inner edge of its path. And even at its closest point, it would still be farther from the sun than any object we've ever sent a spacecraft to visit. This is a planet that exists on the very edge of the sun's gravitational influence, in a zone where space begins to blur into the interstellar void. Finding a super-Earth in this region would solve one of the biggest puzzles in planetary science. When astronomers look at other star systems, the most common type of planet they find is the super-Earth. These are worlds larger than Earth, but smaller than Neptune, and they appear to be the default product of planet formation. They're everywhere. Almost every star we've studied in detail has at least one, except ours. Our solar system, as we currently understand it, lacks a super-Earth entirely. We have rocky planets on the inside, gas giants in the middle, and a sparse collection of icy dwarf planets on the outside. But no super-Earth. This makes us an outlier, an exception. And in science, exceptions are usually a sign that you're missing something. If Planet 9 exists, we're not an outlier anymore. We're typical. We have a super-Earth, just like everyone else. It's just farther out than we expected, sitting in an orbit that kept it hidden from our surveys for centuries. And if it doesn't exist, then we have a much bigger problem. We have a massive gravitational anomaly in the outer solar system that contradicts everything we understand about orbital mechanics. We have objects that are being herded into specific paths by a force we can't identify. And we have to explain why our solar system is the only one in the galaxy that doesn't follow the standard architectural pattern. Either way, the implications are enormous. But here's where things get complicated. Finding an object at the edge of the solar system is not a matter of building a bigger telescope and pointing it in the right direction. The problem is more fundamental than that. It's a problem of light. Most of what we know about planets comes from observing the sunlight they reflect back toward Earth. But light obeys the inverse square law, which means its intensity drops off drastically with distance. By the time sunlight reaches an object, at 500 or 700 astronomical units, roughly 75 to 105 billion kilometers from the sun, it's thousands of times weaker than it is here on Earth, and then that faint light has to reflect off the planet's surface and travel the same enormous distance back to our telescopes. By the time it reaches us, it's almost undetectable. The planet becomes, for all practical purposes, a black object sitting against a black background. This is why standard optical telescopes, the kind that work beautifully for observing Mars or Jupiter or even distant galaxies, are almost useless for finding Planet 9. You can point the most powerful optical telescope on Earth at the exact location where the planet is predicted to be, and if it's far enough away, you still won't see it. The photons just aren't there. The signal is buried beneath the noise of the cosmic background, so astronomers have had to shift their strategy. Instead of looking for reflected light, they're looking for heat, even a cold. Distant planet retains some warmth from its formation. A world with 5 to 10 times the mass of Earth would have significant internal heat left over from the gravitational compression that formed it billions of years ago. That heat radiates outward as infrared energy. It's not much. At the distances we're talking about, the planet would be barely warmer than the surrounding space. But it's enough. A faint heat signature moving slowly against the fixed background of distant stars. That's what they're searching for. Not a dot of light, but a whisper of warmth.